Good morning, my dear kids. In today's class, we are going to discuss some application problems on the motion of charge particle in magnetic field and electric field. Like if there is a friction is there, if there is any viscous drag is there, then how that charge particle is going to move in this combined magnetic and electric field. So let me start the class. Read the question. A positively charged particle having charge Q is accelerated by a potential difference V. This particle moves along the x-axis, enters a region where an electric field E, the direction of electric field is along positive y-axis, so positive x-axis. Some correction is there. It should be x-axis. The electric field exists in the region bounded by the line x equals 0 and x equal to a. Beyond the line x equal to a, in the region x greater than a, there exists magnetic field of strength B directed along positive y-axis. Is asking where does the particle will meet the line x equal to a, and the pitch of helix formed after the particle enters the region x greater than a. I think we are bringing both electric and magnetic field. The question is very simple. Only you have to get back to the basics of motion of charge particle in electric and magnetic field. This yellow color, let me call it as a magnetic field region. Try to work out. Meanwhile, I'll set the diagram. Okay, like this, it will continue for x very much greater than a. So charge particle, it will get accelerated due to, how do it get accelerated? Due to potential difference. So therefore, shall we write QV is equal to m v naught square by 2. What is V? V is the potential difference. So sir, how you are writing this QV? When a charge particle get accelerated by a potential difference, so it will acquire kinetic energy. Suppose say this is the electric field. Not that electric field, this is some other thing. E dash shall call it. So what is the potential? Potential difference will be V. If I release a charge particle here from rest, it will start accelerating. By the time it comes here, the charge particle will acquire a velocity V. Why do it acquire a velocity V? Because it will get accelerated due to this potential difference V. So therefore, the work done by electrostatic force should be equal to m v naught square by 2. So what is V naught in term? 2q by 2qv by m. V is a potential difference through which the charge particle is accelerated. This is very important. I could have directly given initial velocity V. So a student should have an idea that the charge particle will get accelerated due to that potential difference. Okay, no. The charge particle now will get into the problem. It will enter here V naught. This is the electric field. Everywhere here the B bar is in this direction. Till where this is the boundary x equal to a. Now by the time charge particle I think it's correct only. Here this has to change. I'll make some changes. B bar has to change. No, not that one. Some major mistake happened. No, this will be a correct one. This one. I made some changes. Let the B bar be along x-axis, E bar be along y-axis as it is. Now, what is the force that will act? Electrostatic force will act. Fe. Because of this, the charge particle is going to describe a parabolic path. By the time it arrives here, it will have Vx and Vy. Okay, no. So what is Vx? Vx must be equal to V naught. Because the horizontal component of velocity will not change. Then what is the time taken? T equal to 0 here. So let it arrive after some time T1. Then what is the distance it will cover? A with a speed V naught into T1. So T1 equal to V naught by A. Time taken by the charge. This will be a parabolic path. Oh, projectile motion, everyone knows. Okay, then after this, T1 equal to V naught by A. Then what about Vy? How to calculate Vy? Vy shall be right Ay into T1 square by 2. What is Ay? QE by 2m. Okay. Yeah, I made changes. Thank you. Ay equal to QE1. So T1 is A V naught by whole square. Later on, we'll write V naught in the end. So it will become a very lengthy equation. Let it be as it is Vy. So this is the speed Vy now. What about this distance? Is also asking this distance where it will. Let me call Y naught. How to calculate Y naught? Y naught equal to Ay T1 square by 2. Ay is QE by QE naught. Okay, you only will write it. QE by 2m. T1 is AV naught whole square. Vy is equal to Ayt. Okay, this is a Y naught. Then after this, look at a component of field is there, a component of velocity is along magnetic field. Other component is perpendicular to magnetic field. So what can happen to the charge particle? It is going to move in a helical path. So this will be the axis of helix. Rough diagram it is. So the charge particle is going to move in an. First we'll draw the helical path. First I'll draw the axis of helix. No. So you do get plenty of numericals. Sometimes this is one of the best topic where the professors, IT professors will pick up to test student. Like this, it will continue. Now this will be the pitch. This will be the radius of the helix. Time taken to complete one revolution. All the things is asking. So the point where it will meet the magnetic field is in fact directed in this way. The question given little bit different way, so I just changed the magnetic field to be horizontal. Okay, let's get into the all the unknown things. Who will determine the radius? Which component? Mvy by QB. What is Vy equal to? We know here from. Able to interlink all. Then time period of revolution. It is independent of speed of projection. 2 pi m by QB. Time period of revolution. Then what about the pitch? Pitch given by V into Vx. What is Vx? V like a Vx into T. What is Vx is equal to V naught. This is 2 pi m by QB. So what is V naught? V naught is the speed with which the particle will enter at origin. So now, so what are the types of questions? If I vary this potential, accelerating potential V naught will change. Anything will happen to pitch will change. I think match the followings. They may ask you best questions here. So now you substitute that V naught. So this will become 2 QV by M. Like this, you can further simplify this one. So this is the pitch of elixir. You can define the coordinates of the charge particle at any time. Like in previous class, what we did, the same thing you can carry on here also. Anybody having doubt, you can clarify. This will be very topic will be very best questions will come. A student has to should have the 3-dimensional approach, 2-dimensional one. Student effort is needed here. There's no other way student's effort is needed. But everywhere the kinematics, magnetic field comes, we know it should be like a part of a circle or helical path or any other path. You know, in electrostatic field, it'll be parabolic path. Okay, all these ideas is what you have to combine here. I'll go to the next question. Read it. I will move to the next page. We have enough place there to scribble. Read the question now. The space has electromagnetic field which varies with time, whose variation is given as B equal to minus B naught K cap if T less than. So much of information he has dumped here. I'll take out these options. May not be. Some of you are unable to read. Okay, I increase the size. Okay, now you can read it. Just you need patience to work out such problems. Nothing is there. The magnetic field and electric field will vary with the time. So what about the magnetic field? It will be directed into the plane. I think better you have to take this problem in XY plane. Pi m by q b naught. What do you mean by that pi m by q b naught? What is the time period of revolution in general magnetic field? 2 pi m by q b naught. Here, for the interval of time 0 to pi m q b naught, the magnetic field will be directed into the plane. Afterwards, how it will come? It will be directed along negative y-axis. And afterwards, after one time period of revolution, it will become 0. Then what will come? Then the electric field will come. Okay, well, I'll try my level best to give a better diagrams. The magnetic field will be directed into the plane for an interval of time how much? Half of the time period of revolution. Is the charge particle, where the charge particle? Charge particle is here. These are, I'm telling this one, please do work out numericals. I almost around some 20 numericals I have put forward. Remaining few more numericals, you put effort rather than taking teacher's help. Remaining, you have to work out. There's a best problem where you are going to revise kinematics, electrostatics, magnetic field. So many ideas you are going to revise here. No. Anything will happen now. Fleming's left-hand rule. Okay, these are the x and y axis will indicate. This is x-axis. This is the y-axis. This is z-axis. Maximum, try to take help of one-dimensional only. Don't go for three-dimensional. Maximum, try to work out problems in a plane diagram. And then how the charge particle is going to move. The charge particle, B bar, all of you, Fleming's left-hand rule. Left hand, not right hand, left hand. Middle finger in the direction of B bar along into the plane. Like pointing finger into the plane of paper. Middle finger along x-axis. The thumb will be along y-axis. So the force will act in this direction. Because of magnetic force and the velocity, the particle will deviate. It is going to deviate. May not be, actually it should be a perfect semicircle. Yeah. Okay, now to some extent. So it will be here. This is the B bar. T equals 0, it was here. Let's take help of that time. After what time it will be available here? Pi m by q b naught. We know time taken to complete one revolution in magnetic field is how much? 2 pi m by q b naught. So this will ourselves will assume. So after what time it will be at t by 2? Then what will happen to magnetic field? After this time, the magnetic field will become now along negative y-axis. It will be directed. How the velocity of particle will be in this direction? Anything can we expect after this? The motion. How the motion will take place? B bar will be along now negative y-axis. The velocity. How the force? The force will start acting in this direction. F2, F1, I'll write it. Will be better. How the particle should move now? It should move in now xz plane minus x plus z plane. So it's going to describe a path. For what time again? For half of the revolution. Semicircular path. Okay. Then here how the velocity of charge particle will be directed parallel to x-axis. Now after this, the magnetic field will be switched off. After this, the magnetic field will be switched off. To show parallel to x-axis, z-axis. These are the rough diagrams. Maximum student has to develop that thinking ability. Okay, this will be the direction of force acting on the particle. So this will be the radius r. What is r is equal to mv naught by qb naught. And now what will happen? The magnetic field is switched off. So what is it this time? Should be equal to T. No, after this, the magnetic field is switched off. Then what will come into picture? The electrostatic field will come into picture. How the electrostatic field is minus E naught K cap. How the particle will move after this? Minus E naught K cap means the magnetic field will be directed. Now the electric field will be directed into the plane of paper. So he's asking now the coordinate of point on XY plane where it is passing through XY plane again. What is the height it will rise? 2r. And at what distance it will be? I think it will be XY plane is telling. After this, what to do with the problem? The particle will be, what is the z coordinate? So can we write coordinates of this? So let me write this as P1, P2. What are the coordinates of point P1? Will be 0, comma, 2r, comma, 0. What about the coordinates of point P2? Will be x coordinate will be how much? Will be 0, y coordinate 2r, z coordinate 2r. Hope everyone is able to understand. I'm showing the coordinates. Now the electrostatic field will come into picture. How the electrostatic force will act in this direction. So how the particle will deviate and it will go and touch the xy plane. So what is the height it should descend? 2r. Time is asking. So therefore, I think I don't have any. After this, I'll just put the equation. 2r is equal to az t square by 2. What is az? Az is equal to q e naught by m. Az equal to q e naught by 2m. So t square it is. So there's a time taken will be 4 mr by q e naught. What is the time it will take? What is the there's a time. What is r equal to? M v naught by q b naught. We have written, so let's substitute that. One m will come outside, 2 will come outside. Two mq v naught e naught b naught is asking coordinate. What shall I do? In this time, how much of horizontal distance it will move? It will move an x coordinate should be equal to v naught into t. What shall I go for it? This will be x coordinate, y coordinate. Y coordinate is already 2mv, you know, so therefore I'll write it. Okay, this will be further simplification of this will be 2mv naught q e naught b naught. Now what about the y coordinate? Y coordinate is 2r, which is equal to 2mv naught by qb naught. Hope everyone is, I'm unable to further show how it will move in electric field. You are supposed to make assumption of that. And the z coordinate will be 0. This will be our answer. What type of motion it describe is going to describe a parabolic path for this time. Any doubt you can clarify? I'll go to the next question. If you want, you can draw for due to electric field also. We'll take the One more troublesome question I brought it. Gravity is what I'm introducing here. An uniform electric field is present horizontally. Now, what type of path the charge particle will undergo? Let's have a small diagram. Here it is projected. The speed of projection. So the speed of projection, we don't know that. That has to be determined. Okay, let me call that as U naught. So there's a charge Q and there's a mass. There's an electrostatic field. What do you expect this? This should be a parabolic path. We know that it will be it's going to experience an electrostatic force QE, and because of that, it's going to describe a parabolic path. And when it is entering here, and the electric field is present throughout. Here also electric field is present. Here also electric field is present. The magnetic field is present only in this region. So let me indicate so that it will be easy for you to judge what is the problem here. And the gravity is present here. Okay, there's a B naught. Hope you are able to understand. This is what that line AB. Here we have brought that coordinate system, X, Y coordinates. So it will be easy for us, that one. So how do it enter? It will enter with a certain angle. So by the time it enters, it will have X component of velocity and Y component. Why not only X component of velocity? I think because of the, it was projected with the velocity along Y axis, U naught, let's assume that. Then because of electrostatic field, it will get accelerated. So by the time it crosses the line AB, it will acquire an horizontal component of velocity Vx. Now, under action of gravity, magnetic field, and electric field, it has to move in a straight line. It has to move in a straight line means how it should move now. It's going to move a straight line path. After that, the charge particle is going to move in a straight line path. This is a straight line path. For that to happen, for it to move in a straight line path, the net force along X, along Y should be 0. Okay, let's focus more on this particular thing, that one. So what are the various forces that are acting, that are going to act? Mg, electrostatic force, Fe. Then who will balance Mg? Component of magnetic force only. So then let's get into magnetic field. It will have both X and Y component, no? So due to X component of velocity, okay, B bar Vx. So there'll be a force in this direction. Fby, I'll write it. Please, all of you make observation, take Fleming's left hand rule. Then due to B bar and velocity. So here we'll get one more force. I'll take some other colors. Look at these two magnetic forces. I'll highlight it. At least you are able to notice here. Who will balance Mg? This Y component of magnetic force. Who will balance electrostatic force? The X component of magnetic force. So what is Fbx? I think our problem will be solved if we are able to think this much is equal to Fe. So what is FBX? FBX should be equal to Q Vy into B naught. This is the one equation. Similarly, we will balance the weight. If I write minus sign equal to 0, they'll be more justified, no? Then FBY minus mg equals 0. FBY equal to QVX Vx. So this angle should be theta. We don't know. And when it comes here, it will have some velocity, say V. What is Vy is equal to Vy equal to V sine theta? What is Vx equal to V cos theta? Then what is the given thing? Look at this. Take help of it. All of you look at this part. Q E equal to mg, no? So equation, there's the equation 1, there's the equation 2. Given Q equal to mg. So based on that, I'll equate this one 1 and 2. How much will get sine theta? Theta will be 45 degrees. So theta equal 45 degree means, what does it mean? But what was our question? The speed of projection we have to find out. Only there's a thing, no? Nothing. Okay, the one thing I think I have to, regarding G, nothing given, no? So that we have to, I think, take it everywhere. Even I'm too getting confused. G equal to 9.8 is telling, so we have to take it. If he's there only on the right side of AB, okay, they would have mentioned. Okay, we'll do one thing. G, I'll put on either side of AB. Because nothing is mentioned means we have to take on either side. If he has mentioned specifically the G is present only on the right side of AB, we could have assumed it. Okay, till here, no problem. Then what was our, we have to calculate this U naught. That was only our purpose. How to bring that U naught, we have to trace. So one thing we came to know that Vy equal to Vx it is. Okay, let's get into the next part of the discussion. Vy is equal to U naught minus G. Okay, time taken to reach here. T will write it. What is Vy equal to? V sine theta. We can assume it to be V sine theta. V sine theta. What about Vx? Vx is equal to acceleration QEM into T. So Vx equal to V cos theta. Hope I think we can now get into the very easily. Theta we know 45 degrees. T naught. Okay, I'll put it T naught. Lot of symbols are there. Okay, T naught I introduced. Okay, let's get into this one. Theta equal 45 degrees. Theta if it's 30, okay, we could have done that. So theta equal 30 degrees. So theta equal to as 45 degrees. So therefore, equating these two, theta equal to 45 degrees. So therefore, equating this to GT naught equal to QE by M T naught. QE by M will become equal to G. This is very important. I think twice I changed conditions, but I think we have to be very extra careful regarding the gravity. These are very popular. Check the advanced paper, motion of charge particle in electric and magnetic fields. Where any processor can make any of the problem here. So I suggest students better to learn the methodology to solve such problems. Okay, because of that, we are equating these things. Let me take the next question. I'm just presenting few. You have to really put effort in analyzing all such numericals. Now, before this, we'll take this one. Consider a region. I think it's a very lengthy question. Better read once. Native y-axis. I think better draw x coordinate, y coordinate, rectangular coordinate system, then get the direction of B bar. All the fields which are given, get that particular field. Now I need a lot of space to solve this, so I'll minimize it a little bit. Consider a region containing gravitational field and magnetic field as discussed. There's no electric field. Okay, we can manage to some extent. Even I'm drawing diagrams. Okay, there's X field. Yeah, oh, I think we can manage with this. There's a y-axis, there's a x-axis. Now you indicate all the things clearly. What about the gravity? Gravity is present. B bar for x greater than 10 and 0 for x less than 10. Oh, it is present only after certain region. So we will bring a strip. Let's have a condition like this. So this is x equal to 10 meters. So B bar is present only in this region and that too it's out of the plane. I think, okay, maximum now we are, the G in fact will be there everywhere. Okay, let's indicate that also. Let's get into a particle of space projected with a velocity 10 I cap plus 10 G. So I'm going to project with a speed V naught at an angle 45 degrees at t equal to 0. I think problem looks very interesting. So only it's a student has to manage things here. It is like a projectile motion first. It is projected from the origin. Then it's going to enter the magnetic field. Let's see that how it will enter magnetic field. Based on that, the trajectory of particle in the magnetic field will come. Moreover, there's a uniform magnetic field. Okay, let's get into this time of flight of this. We'll calculate. So time of flight of the particle will be 2v0 sine 45 degrees by g. No g. Okay, okay, I'll remove this. Yeah. There's no gravity for x greater than 10. Okay, I'll indicate here. Now, let me highlight it so that'll be very easy for me to read. Okay, there's a 2v0, and what is value of v0? Magnitude of that will become equal to 10 root 2. v0 bar equal to 10 I cap plus 10 j cap. So the magnitude of this should be equal to 10 root 2. Let me substitute that in there. So time period will be 2 seconds. Time of flight. Then what is the range? I think we need a range also. So we know v0 cos 45 into this is time of flight. So v0 is 10 root 2, 1 by root 2, time of flight 2 seconds. So 20 meter is the range, but 10 meter is there. Okay, exactly at half of the, exactly at highest point, it is going to cross. I think the problem is really very simple now. This is V0. Okay, now in what action the magnetic field will act here? Magnetic field out of the plane, so the magnetic force will act downward. So there's a parabolic path. And the magnetic force will act down, like outer magnetic force will act downward. So it should deviate. Okay, then it's going to describe a circular motion. Now the gravity will come into picture. So there's a time. Okay, we'll do one thing. We'll write P1, P2. Time taken to move from O to P1 is half of the time period, T by 2, which will be 1 second. What is time taken to move from P1 to P2? Time period of revolution. Pi m by q b0. So this will be b0 value is how much? To IA. To alpha 2 by alpha k it is. I think that the b bar is 2 by alpha k. Alpha is q by m. Okay, let me substitute all the values. Pi. Okay, this will become alpha. B is 2 by alpha. Total span by particle in the magnetic field region is pi by 2 seconds. Okay, this is where alpha is q by m. Let's get into, I think, okay, we got the option B. Luckily, one option we are at safer side. Then Particle touches the x-axis first time after projection at a distance 15 meters from the origin. Okay, this is 10 meters. This will be the radius, no? So what is the radius? Oh, small r I'll indicate. Radius r equal to mv0 by qb. v0 value 10 root 2 alpha. This is 2 alpha. Oh. Okay, this alpha get cancelled, so this will become 10 by root 2 meter. I think option C not possible. 15 meter, 5 meters. Option C also given. No? Anybody check calculation where I'm going wrong? Speed of projection. Is telling radius 5 meter, but we are getting. Okay, fine. This is correct. Anybody confirm calculations?
Sir, we will be 10, no, sir, because it is only in x. Along y direction, no velocity.
Okay. Somewhere here I went wrong. Yeah, 5 meter will come. Yeah, thank you. So this will be 5. Okay, that will be, I think this will be 15 meter. I'll write it. Okay, I think option C also correct. The particle crosses the y-axis first time after projection with a velocity. Why after this? Oh, it is going to move path like this. Again, it will come like this. Again, due to gravity, presence of gravity is going to describe a parabolic path. Here it will have V0 and this will be Vy. So we know this horizontal distance is 10 meters. So we'll take P3. So time taken to move from P to P3, that will calculate. So T P2 P3 should be equal to V0 into, this should be distance 10 by V0. 10 by 10, 1 second. Then y component of velocity Vy should be equal to G T_P2 P3. 10 into, this will be 10 meter per second. V0 is this one. So what will be the velocity vector? This should be equal to minus 10 I cap. Oh, problem very beautifully framed. Nice problem. Yeah. Okay, option B, C, D will come. I think we need patience, lot of patience. Drawing diagram is very essential. Hope everyone try to understand. So don't get scared anything. First indicate all the fields, where all the field is present, where all field is not present. I think that is very important. Once we get the field, we can easily work out the problem. Unlimited problems you can encounter here. Unlimited, I'm telling this ones. All the answers I'll highlight once, so that will be easy. Make observation. We'll take the next again. One more good problem is there. Write all these things. You write it. Circular path. lot of applications are loaded in my laptop related to app. That's why it is getting stuck, and daily I'm restarting it in spite of that. Okay, I'll go for the next. Yeah, one more very interesting problem. Let's see that how student will really manage this. It's a very simple. Z-axis not needed. Okay, still to confuse you, I brought it. Okay, I'll make the diagram. If they mention gravity, you go for the gravity. Otherwise, not needed. A charge particle of charge q and mass m is released from rest at origin at t equals 0. Find the instance of time at which it touches the y-axis. And the magnetic field region is present throughout that one. B bar is, B is, will write the data. B bar is non-zero for x greater than L. E naught is I'll add this data so that it will be easy for you. And E will be 0. Okay, carry on now. I will give some time. So now the charge particle is released from rest. Is telling the charge particle here will be released from rest. Because of electrostatic field is going to accelerate. And there's a distance. So what is the, for what region the electric field will be non-zero for a distance for a length L. Now it will go to accelerate. When it arrives here, we will indicate L. When it arrives here, what is the state of charge particle? It has acquired a velocity v. Now, very next moment, the field will be discontinuous. Means here electrostatic field will not exist here. The magnetic field will come into existence. This will be, sir, is it practically possible suddenly field non-zero to zero? Let's assume, but practically it cannot become suddenly. It has to gradually decrease here. So we can put some sort of approximations we are doing. Okay, all of you? Let's not bother that real practical situation. On paper, it is. Now the field suddenly here, there's no electric field and magnetic field will come into existence. Fleming's left-hand rule, B bar and velocity. So how the force will be acting vertically up. Because of this, how the particle will move. It's going to move in a semicircle. Yeah, it will be like this. Now it will acquire a velocity. It will emerge with a velocity v naught. Some red color one will choose. Now anything will happen to the electrostatic field. I think it will come into picture. So look at the charge particle. It will get accelerated here. Electrostatic force will act. Because of that, it will accelerate. So let me write V1. Now, what is the state of charge particle? Same say like a V2, but electrostatic force will act in this direction. So here it was acceleration, here it will be retardation. Then finally, the charge particle will come to instantaneous rest. Instantaneous rest here. So this is at t equal to, so this will take origin. There's a point P1, P2, P3. Now again, what will happen to charge particle? Again, it's going to retrace the path. Again, it will enter. So like this, if you look at the charge particle, it's going to oscillate. Hope everyone is able to. Like this, if I extend this, What will happen to charge particle? Charge particle is going to again enter the magnetic field with the same velocity v naught. Like that, it will keep on happens. How long? As long as the magnetic field is present. So here better to show arrow like this. It will retrace path. So P1, P2, call this is P3. So what time it will take to move from O to P1, same time it will take to move from P to P3. So we'll go for the time calculations first. Time taken to move from O to P1 should be equal to L should be equal to QE by M T O P1 whole square. So TOP1 should be equal to 2 ml by QE. I think this time should also be equal to 2P2, P3. What about the time P1, P2? Half of the time period of revolution. So pi m by QB naught. So this will be like some sort of like a periodic motion. No? The particle will go like this. Here first it will accelerate. I think I'm able to describe the complete motion. It is going to accelerate. Now with a velocity v, it will enter magnetic field. Due to magnetic force, it moves in a circular path. Then again it will leave the magnetic field. Now electrostatic field. Due to that, undergo retardation, comes to instantaneous rest. Again the particle will retrace path. Again will go like this. Then again it will enter the electric field. It will undergo retardation, come to instantaneous rest. Again it will accelerate. So like this is going to describe the path here. Find the instance of time at which it, I think we have to generalize it. So time taken to move from O to P1 and P to P3 are same. So in general, we'll call this a T naught. What is a T naught? T equal to 0, it will be here. Don't write capital T time period of revolution we are using, no? What is one T naught? One T naught should be equal to TOP1, TP1, P2 plus TP2, P3. TOP1 is equal to P2, P3. So this will become 2. So these are the instants of time. T naught, 2 T naught, 3 T naught. Initially, you may get scared, but the problem is very simple. So in advance, you may get questions where some earlier problem we have seen, or you may end up with a very simple analysis of this kind. N T naught, we can write it. So that instants of time, N T naught. So where N equal to 1, 2, 3, 4, and so on. Anybody having doubts, you can clarify. If you have anything related to this, you can just put in chat box or you can unmute and you can interact with me. I think all these questions manageable, provided we should read information properly, even myself also. If I don't get the information, means in what action the electric field, magnetic field, no, definitely we may go wrong. These are the some. So in such numericals, what happened? What first priority? The direction of E bar have a clarity. I will show the E bar. Let it be clearly visible for us. Here release from rest. Hope everyone is enjoying such numericals, and if you work out few more numericals, you'll gain confidence and you can manage whatever be the range of question. Let it be, you can manage it. Let me go for the next set of question. Yeah, we'll deal with some friction. I brought it in magnetic field. Let's see that how you. I'll pause it. So there's a charged particle which is projected at a distance a comma 0 comma 0 along positive y-axis, and there's an electric and magnetic field which are directed along the negative z-axis. So that minus b k cap minus naught k cap is what he has mentioned. Okay, let's do one thing. We'll convert this into plane diagram. So the charge particle here, it is projected with a speed v naught. This is y-axis. This is x-axis. Let's have this much of data. We'll see. Then how the magnetic field will be into the plane. How the electric field, it will also be into the plane. We'll convert into plane diagram. Then one more diagram, rough diagram, you can keep it. If the block is, there's a rough horizontal surface. So what are the forces that will be acting? mg, electrostatic force, q e naught, then the normal contact n. I think this also needed. So what is n is equal to normal reaction, n equal to mg plus q e naught. Then what direction the friction will act, and there's also magnetic force. So let's get into electric field will be acting into the plane of paper. Let's get into magnetic field. Fleming's left hand rule, B bar V naught. Okay, there's a magnetic force is acting here. Then the friction will also act. Now tell me what can happen, what will happen to the particle now? Friction is a resistive force, dissipative force. So the speed of particle will keep on decrease. So here, what this friction will do, it will produce this magnetic force will provide required centripetal force, and the friction will retard the motion. Very simple analysis what I'm trying to do here now. The magnetic field force will try to provide required centripetal force, and the friction what happen will provide a tangential retardation. So let's write the equation. What can be the path of particle? So first we'll get into the mathematics. So here q b naught v should be equal to mv square r. Small r, I'll write it. They'll be more meaningful. Speed of the particle at any time. So we are getting one equation of like this. Then tangential retardation. So what is the tangential retardation? F equal to minus mat. So this should be equal to mu n m. At should be equal to dv by dt. So what is the question? The time when the particle will come to rest, time when the particle will hit the center, distance traveled by the particle when it comes to rest. ABC, the time taken. So when it will come to rest, when the speed has become 0. And what is n equal to? We have the value here. So let me first get the if you want this m also, I'll send here. What has to be done now? Limit. At t equals 0, what was the projection of? It was projected with a speed v0, and finally it has come to rest. So I'll finally end up with equation mu I think better let m be there. mv0 by mu mg plus qe0. What is this t? Time taken by the particle to come to rest. Let's find out some quantity so that we can further get into problem. Time taken by the particle to come to rest. Okay, after this, time when the particle come to rest. Okay, first part got over. Okay, we are very happy now. Let's do one thing. Time when the particle will come to rest and time when the particle will hit the center. What do you mean by center? Yes, sir, can you show us the path? Yes, the path is what I'm going to bring here. No, all of you make observation. It is going to be a plane spiral. Now, what is the question? What you can ask is like, sir, how come you say that it will come to rest at origin only? There's the primary question everyone should ask here. SS, there's a million word question. Actually, that the data should be given AMV not equal to QB not. Then only it can come to rest at origin. Otherwise, not possible. Center is telling I am choosing electron. So let this be given. Sir, how come it will come to rest at center only? So it's a very simple. I don't want to mess up things. So what is the radius of the circular path? MB naught by QB naught. Let's assume that at any instant of time t. When V0, what will happen to the charge particle? When particle has come to rest, what is the mass of particle? Remain constant. Charge of particle remain constant. The magnetic field strength, it also constant. So if V0, then what should become 0? R should become 0. So therefore, finally, where the particle should come to rest at center. So E should have given this. Otherwise, not possible. It may, if maybe this is equal to condition. So this has to be given. I'm introducing this. Otherwise, it will be meaningless to confirm that it will come to rest at origin. Okay, all of you. This data should be given. Then okay, then we can conclude here. Yes, it will come to rest at the origin. So what is the simplest reason? Because m, q, b naught, they are the parameters which will remain constant whether the particle is at rest or in motion. So therefore, when the particle has come to rest means the R should be 0. R should be 0 means you should come to rest at center. Hope everyone is able to understand here logically. When V 0, then R should be 0. What is R? The radial distance of the particle from the center. So when it has come to rest means it should come to rest at center. I'm trying to give a reason of like this. So it'll be like a plane spiral. What you have to call this. Is it angular momentum of particle conserved? So many things are there. We can angular momentum of particle conserved. No, there's a torque is acting all the time because the speed of particle will continuously decrease here. No. So can you show at any instant any diagram so that we will get some picture? Yes. Okay. I'll do one thing. So this will be your force, which will probably require centripetal force, and here the friction will act. And this force will be directed towards center. Okay, the time, I think both are same, no? Time taken by the particle to come to rest and time taken by the particle to reach the center. Center or will write origin. What it should be called again same time, that same time only, that one. No, after this, last one, distance traveled. How we can find out distance traveled? I want most of you know kinematics, we were in better position. Anybody, can you suggest distance travel?
Velocity into time.
Speed into time. Okay, try. No, okay. Velocity into time, can you make it? Speed into time.
Speed into time.
Yeah, there's the only thing. Okay, can you work out now? I think it will be a little bit, still will land in trouble. He's asking total path length. There's a problem here. I want your law, kinematics and laws of motion into the picture.
Sir, acceleration would be constantly decreasing now, sir.
So,
So we can use v square minus u square is 2s.
oh God, like you are killing total kinematics. Huh? Is it decreasing at a constant rate, velocity? Acceleration is variable. No, variable accelerated motion. How you can apply equations of motion? Okay, yeah?
Yes, sir. Yes.
We should not think like that. Okay, fine. Okay, no. See, you have done variable accelerated motion. Go back, kinematics, variable accelerated motion. Tell me what you do. V dv by ds. V dv by ds. So the retardation, so the next part of the problem will be, we know F equal to minus mat. This is equal to mu n minus m. A tangential, this A tangential, what we can write it as V dv by ds. S is path length. So this will become mu, and n I'll substitute later on, no problem. So this will become ds equal to V dv. At initially, okay, let it be this one, and initial velocity is v naught. Finally, it will come to rest, and the total path length, let me call s. S is not displacement, so let me write here, this is s only, will take it. So this will become mu n m s equal to v square by 2 v naught 0. The value of s is needed, so this will become m v naught square 0. Okay, here also 2 mu n. What is the n we assumed it to be equal to mg plus qe naught. Path length, just right, path length of charge particle. Okay, so there are many ways you have to really go back to all your basics. Even for me also applicable, not only for you, for me also. I should not try to do anything very big research. Hmm? Angular momentum of particle, not conserved, no? So we'll write it here. Angular momentum of particle. Angular momentum of particle is not conserved. What about kinetic energy? It's also not conserved. Why it is not conserved? Because the tangential force is acting, no? And we know MVR, angular momentum equal to MVR of a particle, and continuously the speed is varying, R is also varying. So therefore, as the net torque is non-zero, no? So even the angular momentum also I can ask you. Okay, so one more we have. Yeah. I'll put it in corner. A particle of mass m and charge q is projected from origin with a velocity v equal to v naught I cap in a non-uniform magnetic field b equal to minus b naught x k cap. Okay, look at the magnetic field. It is going to vary. So now what we are discussing the motion of charge particle in a non-uniform magnetic field. Here, b naught and b naught are positive constants. Find maximum x coordinate of the particle during its motion. Who can produce such a magnetic field? Many wires are, many current carrying structures are there. They will produce such a magnetic field. Let's not bother. It is projected from origin. So try to assume that field is a variable one. It is projected from origin. Okay, this is the XY plane. It is projected from origin with a velocity v naught. Now what will happen to charge particle? Look at the b bar into the plane. Okay, everywhere b bar is into the plane. I'll show it here. And that magnetic field is going to vary along x, non-uniform magnetic field here. So from Fleming's left-hand rule, b bar velocity, so the magnetic force will act here in this direction. Call say like a disposition. Let it be say some f naught initially. It's like a, for just greater than x greater than 0, the particle will start moving. So it will experience a magnetic field. That's what here. So at x equals 0, field should be 0, no force. Just x greater than 0, limit. Just x non-zero value, very small infinitesimal change in x will result in a magnetic force, and because of that the particle starts deviating. If the field were uniform, it would have described circular path. It would just describe the circular path here. If field very uniform, but field is non-uniform, what do you expect? So go for r equal to mv naught by qb. I think we have to now really analyze it rather than jumping. So as the particle, we know what happened to speed. Magnetic field work done by magnetic force on a moving charge particle will be 0. So nothing will happen to speed of particle. But here, look at this one. As it moves, the B bar will increase. So R should decrease. Suppose this radius is somewhere here. So will it be a circular path? No, it cannot be circular path here because R is variable now. So it's going to describe as some curved path. Rather than going and just drawing some writing equation, student has to analyze from here. The work done by magnetic field is 0. So therefore, the speed of the particle will not change. Put it V naught. Then as B increases, R will decrease. So what is the path it is going to describe? It's going to describe now a curved path. The trajectory will be such that the radius of curvature is going to decrease here. So maybe it's a very big circle is there. So it's going to go like this here. Means here we have to say there are so many things are there where you have to fight with the idea here rather than writing some equations. So if radius were constant, it would have been like this, no? No, if B were constant, if B decreases, B increases, R should decrease. So what do you expect the path? Path is something of like this, no? So hope you are able to understand what we are finally trying to do. If B were constant, this is for path if B increasing. So is it a circular one, the red color one? No, it's not a circular. This is some curved path here. Sir, why it will move curved path? Why can't go straight? Because there is a magnetic force. There is a magnetic force. Now, what should be the path? Okay, let's get into the kinematics idea. Because of force and velocity, will it just move along horizontally with velocity, or will it move in the direction of force? So some resultant path. So it is going to deviate from the velocity vector. So here is what, with all that, I'm, but not a circle. You can see that. If I further continue, but don't show it to be circle. Okay, I think it's nowhere circle. No, it's nowhere in this like a circle. And now look at this, the velocity, but the speed of particles should never change. No, okay, somewhere let me take a very good problem. Actually, you need some half an hour, not like 3-4 minutes. Also not possible to crack. To be frank. Maybe I'm slow learner. I took half an hour first time when I'm doing this problem. Maybe it happened with me. Others I don't know. So the speed will remain as it is. Okay, this is theta. Now what will happen? How the magnetic force should act perpendicular, always perpendicular to the path. The speed of particle will remain same. Okay, this is x comma y, will write it. And now you can ask questions. So why can't it go like this only? Why you are making it something curved here? Why it will have some turn here? See, all the time at this point and this point. So no, the radius you don't put small or anything, capital R. The radius of curve will be varying. It is some sort of curved path here. Now at one instant, you look at this particular thing. Here how the particle the magnitude will be continuously varying. So even the magnetic force which is acting, it should change centripetal force because the radius of curvature is going to be different at different points. Let's get into this one. So altogether, look at the particle. So shall we say that there is some sort of acceleration earlier the x component, y component of velocity was 0 initially at point of projection. It was projected horizontally. Somewhere it will take a curvature like this. Here, what happened? The x component has become 0. But sir, magnetic force can do work. No, it cannot do work. But it can accelerate a particle. It can change the direction of motion. So here, what this magnetic field has done, it has made its velocity vector to get directed along y-axis. So shall I put like the x component earlier was v0, now it is 0. And this is what that maximum displacement, what we needed. Sir, how you can say maximum displacement? After this, the charge particle again, the position of charge particle from the origin, the x coordinate will decrease, no? So among all this, there's a maximum displacement. Tell me at maximum displacement, what conditions will arise? The velocity of particle is along positive y direction. I think there's a core central part of our discussion. At maximum, I'll shift it here. Yeah. At maximum x displacement, at maximum displacement along x-axis will write along x-axis, the velocity of particle will be directed along positive y-axis. Then only that will become maximum, no? Sir, okay, fine, sir. Everything is fine. Okay, we'll agree with you. Why do the charge particle will move like this? That's what I'm trying to bring here. So let's assume that one. If it is moving in circular path at one instant, how the velocity of this will be? Can it happen here? Here the velocity was x-axis. Now the velocity is along y-axis. Same thing for curved path also this is. At one instant, the velocity will be directed along y-axis. That will be the maximum x coordinate. After that, again you see that here, again it is not at maximum distance from the origin along x-axis. So therefore, at maximum x displacement, this is a condition that will arise. I think this is very, very important. That comes from here only. The idea comes from here only. Okay. Okay, now let's get into the mathematics here. After this, let's get into kinematics. Then acceleration along y-axis is equal to FB cos theta by m. What is FB? QVB by m into cos theta. Now, what is B? In fact, this is Q V naught. Okay, let me return that V naught. Q V naught B naught x cos theta by m. Can I write this as AY as dVy by dt? But we want x coordinate, no, what to do with Vy? So this, I'll adjust some. Let's see what to do with cos theta. Huh? Dvy by dx. Dx by dt, what should we write? V naught cos theta. There's a reason, no? So like this we write it. So V naught cos theta will get eliminated. So we'll end up with dvy by dx is equal to, let me write here only. Further, okay, can we integrate now? Q B naught m x dx. What should be the limit now? at x equal to 0, the y component of velocity is 0. You can see clearly from there. Yeah. Then at maximum displacement, what is the y component of velocity is v naught. So solving this, v naught is equal to q b naught by m. So finally, our answer is 2m b naught by q b naught. There's a one rare problem. It's there in IDO. That's why I picked up all possibility of asking as it is. In books, two or problems are there. Try to think on them. Motion of charge particle in a variable magnetic field. You can see the complete description. Of all, I feel this is the important idea of the rest all mathematics. Even this is also an idea. Okay, almost I think I have brought some around 7 good numericals. I think it took a lot of time. So all these are very good numericals are there. So try to think on them and pick up some more best numericals where you can work out on them. Okay, kids, like we had the discussion of motion of charge particle in the electric and magnetic fields, even gravity I brought, some friction I brought, some even the conservation of angular momentum we have brought it. So try to pick up some numericals of this kind, motion of charge particle, and see that how the charge particle will move. But everywhere, the work done by magnetic field will be 0. But the magnetic field can accelerate a charge particle. I think this is something very important. Electrostatic field can accelerate and also can do work. So keep all these energy aspect also in the mind and try to work out. And the maximum problems are based on simple kinematics. Okay, so tomorrow we'll come with the Ampere's force. We'll discuss the topic of that one. Okay, thank all of you. Take care. Bye. See you.